We're looking at F equals BIL here and V equals BLV. Again, here 12 formulas that we want to have a quick look at. F equals BIL is to do with the force on a current carrying wire. So if we've got the old magnetic field going into the page like this, and we now have got a wire that comes along. We'll do that wire in red if we like. Oh no, I don't like to use red on my videos, do I? But we can do that. So we've got this wire, and we've got a current flowing through it. Now we just learned in our previous video that F equals BQV, or we learned it last year. So that means if you've got the velocity of a charge moving in a magnetic field, it experiences a force. So we've got a whole bunch of charges in this wire, right? And I think we learned when we were doing the first part of this electricity unit, DC, that there were something of the order of 10 to the 19 electrons per cubic millimeter. Huge number of charges in a tiny little bit of wire, right? So these charges, when you have a velocity, see, these aren't moving unless we hook them up to a power supply. And so if we were to make the let's have a look here. If we're going to pretend it's positive current, then we'd make this a positive and we'd make this a negative, right? So this would indicate the current. We know the electrons are going the other way, but let's just stick with that. So we've got our fingers giving us the field direction down. This time our positive charges are moving up. So this whole wire is going to feel a force this way. That's the force. How do I come up with the F equals BIL? Well, let's have a look. I'll obviously do that one a little bit later. Well, F equals BQV. We've got that. That's a starting point. Often the way you figure out stuff is you try and do some substitutions. Let's think of some things. What's got Q in it? Well, I equals Q over T. So we could say Q equals IT, V. Look, we've already got that. Can we do any more substitutions? Well, velocity equals distance over time. So we could put this as BIT, distance over time. And look, our times cancel. So we've got this as equal to BID. But we can call D just the length of wire in here. It was just the distance over which we were doing a time for the velocity of the electrons. We know the actual electrons move pretty bloody slow, actually. But so we write this as BIL, and it gives you the total force. It's like you've added up all the electrons and figured out the force. It's very nice. So that's how we come up with that, the force on a wire when it's got a current flowing through it. This is going to be our motor, all right? This produces a motor effect. When you've got a current flowing through a wire in a magnetic field, you experience a force. Now, there's the opposite type of effect, the generator effect, where the second equation comes into play. V equals BLV. This time, you're moving the wire in the magnetic field using some other force, like gravity or your arm or something, or your fingers pushing it along. So this time, we've still got it. I always do my magnetic fields into the page. It's easier to point my fingers in and out like that, right? So this time we've got our wire, and we are moving it. So, actually like that, but we're going to move it that way. Let's see what happens. This time, when we move the wire, what we do is we say, okay, moving the wire that way, positive charges are all going to be moved up the wire, right? So all the positives are going to land up there, and this is going to leave a surplus of electrons down there, right? Nice. So you're expecting this to generate a voltage, and it would have a positive at the top and a negative at the bottom. Very nice. This is just used the Lorentz force law, right, to work that out. So, and that's why I said this law is very important. So now we've got that little bit. Where does this come from? How do we actually work out the voltage? Remembering that this is velocity and this is volts. Well, what stops the voltage becoming infinite? You may well ask that. What actually stops it is the electrical force. Remember, F equals EQ, E being the electric field. So you've got a magnetic force, F equals BQV, pushing these positives up, or the negatives down. But as they pile up, they repel each other, and that's an electrostatic force. So this is the electrical force here, and this is a magnetic. And when they are equal, there's going to be no more movement of charge, and we will be left with our final voltage. So what we can say is that EQ must be equal to BQV. So we can immediately cancel out the Q's. Remember, this is velocity. So what's that leaving us with? But remember this one, okay? We've said that voltage equals ED, right? So voltage equals ED, E equals voltage over D, right? So we can go voltage over D equals B velocity. So we can then multiply that D up here. And we've got voltage equals B velocity D, which is the same as our initial equation, which was B, L instead of D. That just means length. And V, velocity. And that's our voltage. So that's where the equations come from, and you can see F equals BIL and V equals BLV both came from the Lorentz force law. Both easy to figure out. Now, this is a generator effect because it actually produces a voltage. This becomes like a battery with a positive up there and a negative down there, just because you moved a wire through a magnetic field. That's enough on that one.